All right, so we'll talk linear discriminant analysis. This is basically a Bayes classifier with a bunch of assumptions. Okay, and so the idea is this: we have our data. Our training data is labeled, right? So you got classes in this class, and you have observations in another class. And basically, we make a distribution of the variable, the predictors x, based for each class. So we say if the predictor is those that default, what's the distribution of balance? If, and if we're talking about the predictor is balance, for those that do not default, what is the distribution of balance type of thing? Okay? And then we use Bayes' theorem to figure out what's the probability of default given balance. Okay? So from our data, we say, all right, we know who defaulted and who didn't. So we can figure out what's the distribution of balance for those that default, what's the distribution of balance of those that did not default. So we figure out those distributions, and then we use Bayes' rule to kind of flip things around. So Bayes' rule says probability of A given B is the probability of B given A times the probability of A divided by the probability of B, right? So that's it. So this is a Bayes classifier. With linear discriminant analysis, we're going to make a few assumptions, which I'll explain in a moment. But this is basically what we're going for, right? We want to know what's the probability of the class y equals k. What's the probability of y equals k given the data that we have right now? Okay, so if we know that the balance is 2000, what's the probability of default? Okay, something like that. Okay, and so the way we do that is we use Bayes' rule, and we say this is going to be the probability of x given y. Okay, so this is kind of the distribution that we estimated. We said, if we know for those that defaulted, we know what the distribution of x is. For those that didn't default, we know the distribution of x. Okay, we're going to multiply that by the probability of y equals k, which is just, before we know anything, what's the probability that someone's going to default? That's what we call the prior. Okay, the prior probability that an observation comes from class k, and we're going to abbreviate this as pi k. All right, so this is just often we just take the count of observations in class k divided by the total number of observations. So before we look at anybody, what's the probability that someone defaults? Overall, the rate of defaults is around 3.3%. So our prior probabilities are going to probably be around like 3.3%. Question? Yeah.
What's meant by class when you say class K?
Class K is just whatever category. Yeah. So you've got. So in our case, we have two categories or two classes, those that defaulted, those that did not default. But whatever else, it doesn't have to be just two classes. It can be 6 classes and things like that. Okay. And and then over here, this part on the other part in the numerator, x probability of x given y, we're going to just call this f of x, f sub k of x, and this is going to be the density function of x for an observation that comes from class K. Okay, so we have to make assumptions to get a density estimate. Okay, so we have to assume that the density has this form or something like that. We're trying to estimate what the density function looks like. Okay, and so for linear discriminant analysis, we make huge assumptions. Maybe they're good, maybe they're not good, but they work a lot of the times. So I guess that means they're okay. And then lastly, in the denominator, we've got probability of x equals x. This is what we call the marginal probability in Bayes' rule. And we can get this, really, the purpose of this thing in the denominator is to make sure that the whole thing is a probability, which means that it has to be between 0 and 1. And if we added them up across all possible values, they add up to 1. Okay, and so we find this by basically calculating the numerator for every possible category or every possible class, and then we add them up. Okay, so if there's two possible classes, those that default and those that didn't, we do it for both cases, and then we add them together, and that's going to be our denominator value. And that just makes sure that the value that we get is a probability, and that, you know, across both possible outcomes, they add up to 1. Okay, and if you had 5 different possible classes, then you have to find the numerator for all 5 classes, and then you add all 5 values up to get the denominator. Okay, so basically this thing, we can rewrite this to look like this. Okay, so the prior probability is abbreviated with pi sub k. This part, the density function of x given a certain class, is going to be f sub k. All right. So this is the numerator, and then the denominator is basically the numerator for all k classes, all capital K classes, and then we add them up across all possible classes. Okay. So that's all. Equations always look scarier than what they are, I think. The concept is not too bad. And in reality, we don't even have to be scared, because we're not going to do any of this anyway. We just ask the computer, do linear discriminant analysis. We just type in LDA, do this job, do your job, computer, okay? So in 102B, I make you guys do the math and stuff. But in this class, we're just kind of getting exposure to all of these different things, and we let the computer do the heavy lifting for us, okay? All right, so the big assumptions that we make is that the function, the density function, is Gaussian, okay? We're going to assume it's a normal distribution, okay? And then the other big assumption is that the variance is going to be the same for all k classes, okay? So those are 2 big assumptions. All right. So anyway, this probability density, if we have one predictor, so here we're gonna like predict something, you know, predict the class based on the one value, okay? Assuming, so the one predictor, it has to be numeric and has to be reasonable to assume that it's Gaussian, okay? We're gonna plug it in like this, and the Gaussian, the normal density looks like this. In R, you can just use d norm, okay? And so you say d norm of x, where the mean is equal to mu and the standard deviation is equal to sigma. That's what we do, okay? But this is this, right? You don't have to write this down. I mean, you can. I won't stop you. But. Okay, and again, this thing looks messy. All I'm doing is I'm just replacing f sub k with d norm, okay? Or the probability density. That's all I've done. That's all I've done. There's nothing scary going on, okay? And then here, you know, the mu changes for each class, but sigma is the same for all classes, okay? And then, you know, if we took the if we took the log of this thing, and, you know, we eliminated terms that were common and stuff like that, you end up getting this, okay? If you take the log of this thing up top, okay? And then basically, we're going to just assign it, so wherever this value is biggest, okay? So basically, you know, we could do this and we would get the, you know, the probability, and whichever one has the highest probability, we would assign that observation to that class. Same idea, okay? If we didn't want to have to plug everything into here, we can just do this. It's not that big of a deal, okay? And again, really, we just ask the computer to do it for us, okay? I know right now all I'm saying is like, just ask the computer to do stuff. And so as I was thinking about this, I was like, how am I going to write a test if every time in my class I'm saying, well, just have the computer do it, because that's not going to make a good test, because your answer will just be, let's have the computer do it. So So this is what I'm thinking. Yeah, no, not a take-home test. Okay, so you have your final project, which is where you have the computer do it for you, right? So you have that to build your model and stuff. And I'm thinking, you know, I'm going to reveal all the details of the final project next week during week 3. And I'm thinking I actually want to have like 2 competitions, one which is a regression competition and the other is being a classification competition. And you'll enter both, and then, you know, part of your grade will be based on your relative performance. So if you did great on one but bad on the other, like it'll average out, okay? And if you did bad on both, then yeah, maybe, excuse me. If you do bad on both, then yeah, maybe you're not the best student in terms of making predictions and stuff, but still a wonderful human, okay? But as far as the competition goes, you know, but that's okay. But I figure, you know, we'll kind of split it, because I think the both problems could be interesting, a regression one and a classification one. So that just is more work on my part for finding good data sets and stuff. So I'm still working on that. Okay, but then as far as the final exam goes, I think it's going to just have to be like all the conceptual questions from the different chapters, okay? And I know, it's like, is that harder? Yeah, I know. Well, it's harder than saying let the computer do it. That's for certain. Okay. So so be sure you study all the conceptual questions at the end of each chapter in the textbook. Okay. That's probably going to be your question pool for the final. Okay. I mean, maybe like with a few modifications, but probably a good place to start there. So I think that's where we're headed. Okay, so anyway, this is what it looks like. With one predictor, we have 2 Gaussian distributions. This thing is assuming both classes have equal probabilities. Okay, so this is not the credit default example. Credit default, one class was only 3% and the other class is like 97%. Okay, this one's assuming we've got 50-50% probability. Pi 1 is equal to pi 2. Okay, and over here we've got one distribution where the mean is negative 1.25 and the other distribution where the mean is positive 1.25. And they have the same variance, okay? And so if you have something like this, then the linear discriminant boundary is basically going to go right here in between the two. And this is basically, you know, on this side of the dotted line, the probability of being in the green thing is higher, right? The density function here is higher. And over on this side, the density function is higher for the pink, okay? If the pi's are not equal, like if one has a lower probability and the other has a higher probability, then that would basically make one of these density functions taller and the other density function shorter, and that would shift where kind of this threshold line is drawn. Okay. So anyway, this is kind of what that looks like. You know, the hardest part of LDA is figuring out what you know, in this thing, what the f sub k of x looks like, what that density function looks like. You know, what we're saying is we're going to make our lives easier by assuming it's Gaussian. We're going to assume that it's a normal distribution. But that could be a bad assumption, okay? And if it's a bad assumption, you might run into problems. A lot of times, like empirically, as far as it goes, a lot of times it works pretty well, okay? It's, so, you know, again, in all of statistics, we're forced to make assumptions, and generally assuming something is Gaussian is not going to be the best assumption, but a lot of times it works out, okay? Because Gaussian basically means most values are near the middle, some are higher and some are lower, which is usually true for most situations. Most people are somewhere in the middle, and some are higher and some are lower. And so for a lot of times, the Gaussian assumption, even if it's not completely correct, works out. And so the answers, okay? And then the other part is that we're assuming all the variances are the same. And by assuming that it's Gaussian, we only now have to estimate the mean and the variance, okay? We only have to estimate these two things. Well, basically the mean of each class, so you have however many classes you have to estimate a mean there, and then one variance for all the data, okay? So the mean for each class is basically just the mean of each class. You just say, well, which observations belong to class K? And then you take the mean of those observations. So that's about as straightforward as it gets, right? You say, in my data, these 20 people belong to class 1. What's the mean of these 20 people? There you go. These 50 people belong to class 2. What's the mean of those 50 people? There you go. Mu sub 1 and mu hat sub 2. Okay, and then the estimate of the variance is basically the squared distance from the mean values that you estimated. Okay, so it's kind of like the variance, squared distance, average squared distance, except you do it for each class, and then you do it for all classes, and then you kind of take the average of all of these things. So you say, for these 20 observations in group 1, what's its estimated mean? That's going to be your mu hat sub 1. And then you say, what's the squared distance from here? Okay, and you add those up. You do the same thing for everything, all the observations in group 2. You add all of those up, and then you add them together, and now you have 70 square distances from each mean, and you divide that by 70 minus 2, 68. Get your kind of your average square distance. Okay. All right, and then the prior probabilities, the pi hats, the pi's, we just say, well, how many observations belong to, what's the proportion for each class? So if you had 20 and 50, you'd say 20 divided by 70, 2/7 versus 5/7 or something like that. Okay, and again, so that's what we do there. If you have multi-dimensional data, same idea, except now we have a multivariate Gaussian, right? Have you guys covered the multivariate Gaussian somewhere? Okay, anybody not do the multivariate Gaussian? So the normal so you got, we'll go to Wikipedia. Can I close this? I'm going to close this. Oh, wait, you didn't do it?
Yeah.
Oh man, I just closed it. Okay. All right. You'll be fine. All right. Okay, so we'll go to normal distribution. Okay, so here's the PDF of the normal distribution. And then let me do multivariate normal distribution. Okay. I just want to show it's like the exact same thing. Okay, so here we have the PDF of the normal, and this is the PDF of the multivariate normal, okay? So if you look at this, we've got 2 pi sigma squared, and here we've got 2 pi raised to the k, okay? K is how many variables we have, and then instead of sigma squared, we have the determinant of sigma. The sigma is the variance covariance matrix, okay? If you only had one variable, then this is just a 1-by-1 scalar, but now that you have multiple variables, it's a scalar matrix. And then over here, you've got basically e to the x minus mu squared divided by 2 sigma squared. So because it's matrix notation, you basically have x minus mu transpose times x minus mu around the sigma inverse, which is basically like divide by sigma squared here. times 1 over 2. So anyway, this is the multivariate Gaussian. So the multivariate normal distribution, the property is that, you know, when you plot it, it's going to look like an ellipse. But if you look at just one variable at a time has a normal distribution. Okay, so each variable, if you deleted, you know, this variable and everything just kind of dropped down, it's going to have a normal distribution. If you deleted this variable and everything just lines up, you're looking only at one variable, it's going to also have a normal distribution. And then together, you're always going to get this elliptical looking thing, okay? Maybe a circle if they have the exact same variance and no covariance between them, but basically some kind of ellipse. Okay, so with the multivariate Gaussian, you now have a variance-covariance matrix, and we're still assuming that the variance is going to be the same for all the classes in linear discriminant analysis. Again, maybe that's not a great assumption. Okay. So here, the way we run LDA on the computer is we call library mass, which has the LDA function, and then we basically, it's like writing an LM, except you write LDA and you say default as predicted. This time we're going to do balance plus student. We're not using income as a predictor. Okay, data comes from here, and then we can say, okay, what's your predictions on whether somebody defaults or not? And so we just say predict based on this model, and I want the class, and we're going to get yeses or nos. Okay, and then this produces what we call a confusion matrix. Okay, and so this says what we predicted versus kind of the true. And so here's the actual, whether they defaulted or not in the real data set. Okay, and what we see is that when we predicted no, that they really were no's 9,644 times, but we got it wrong 252 times. When we predicted yes, we got it right 81 times, but we got it wrong 23 times. Okay. I think I didn't. I should probably write a little bit more about this. Okay. So on our confusion matrix, basically where the no aligns with the no, those are correct, and the yes aligns with the yes, those are correct. And then the other elements, the 252 and the 23, those are wrong, okay? Those are misclassifications. So our error rate is 252 plus 23 out of a total of 10,000 observations. So that's a total of 275. Out of 10,000, we have an error rate of 2.75%, which seems pretty good. But if we think about it, it's also not super great, because if we look at just how many defaulted in the real data, only 333 people defaulted, okay? And so if we have a null classifier, okay, basically, it's not a classifier. We're just going to say no one defaults ever, okay? This is not a classifier. It's just assuming no one defaults. What's our error rate there? Our error rate's only going to be 3.3% anyway, okay? So our classifier only does a little bit better than having no classifier ever, okay? And so maybe this isn't that great, okay? So, you know, I'm going to jump over here because I didn't finish all of my notes here. I want to talk about the sensitivity and specificity here, okay? So there's you know, whenever you're kind of trying to decide something, if something is you know, true or not true or something. We're predicting a class here. We have you know, sensitivity and specificity. All right, and so here's a picture. Okay, there's a few things. Okay, there's like precision and recall and stuff like that. Okay, so sensitivity is also called recall, and it is, let me draw this picture here. I should probably just copy this into my slides. It's public domain use. These are the selected elements, okay? And these are, this is what we select, and these are the ones that we're interested in. So these might be, so everybody here on the left-hand side, this could be classified as people who default, okay? People who default. And if we identify, we're going to select people, we're going to flag some people as defaulting. And within that, we got people who really do default, and those are the true positives. But then we're going to say this person's going to default, but they don't. They make their payments all the time. Okay? And so those are false positives. That's like somebody that, you know, we should have given them a credit card, but we said, you're too much of a risk, I'm not going to give you money. And we miss out on interest on that customer, right? We could have had a customer, but we turned them away, all right? Whereas over here, we've got false negatives. And these are people that we said, okay, I trust you, you're gonna pay me back. Let's give you some money. I'm the credit card company, I'm gonna give you some money. I trust you, you'll pay me back. And then they don't pay me back, right? They go buy their giant TV and then they say, well, can't pay you back, sorry. And then I go, oh, I lost a bunch of money, right? So that's also a bad thing, right? So if I'm the bank, okay? And so those are the false negatives. So the sensitivity basically is a measure of what percentage of everybody are you correctly identifying, right? So it's kind of the ratio of the true positives over everybody that should be flagged, okay? So here, the sensitivity is you know, what percentage of people who truly default are identified by our classifier as that they will default. So so in our notes, what is that? Okay, so of the people that will default, so there's a total of 333. How many did we say will default? How many did we select and predict that will default? $81 out of 333, right? So in our diagram, maybe I'll draw this, right? So how do I do this? Can I copy this image? All right, let's open up this thing here. Okay, so we'll paste this picture here. All right, great. All right, so what we have is, okay, so here this is, we have a total of 333 default. And then 9,667 no defaults, right? And then here we have 81 predict yes. Predict default. Okay, and then here, and that means we have 252 that were not predicted, right? True negatives, here we have 9,644, and then here we predicted 23, okay? So our sensitivity is equal to 81 divided by 333, which is, what is that? 81 divided by 333, 0.243. So not very good. Okay, our specificity well, what is our specificity? It's going to be 9644 divided by 9667. Okay, so this is like 0.998. All right, so I'll throw this in our notes here. All right, is that all right? Okay, and so we might want to do something different about this. We might say, you know what? I'm not. So here, the kind of the default, the regular setting is that we're basically saying, you know, if the probability is over 50%, we'll predict them as yes, and if it's below 50%, predict them as no, type of thing. This is how we're predicting. But maybe what we need to do is we need to say, you know what? As a bank, which one is worse? I'm in the business of trying to make as much money as possible and lose as little money as possible, right? So as a bank, would I rather make false negatives or false positives? So which, if I'm the bank and I'm choosing who I'm going to lend money to, would I rather have more false positives or more false negatives? So let's think about who these people are, or what the consequences of these things are, right? So I'm a bank, I'm like gonna lend money. Would I rather have someone say I can't pay you back, or would I rather turn away a potential customer because I wasn't sure, because my prediction was bad? So would I rather turn away potential customers, or would I rather approve a loan that doesn't get paid back, or approve a credit card that doesn't get paid back? What would you say? So okay, so I'm hearing both answers, right? Okay, so banks generally fall to the side of saying they'd rather make false positives and turn away customers, okay? Because the money that they lose by turning away a customer is interest, okay? They're going to lose money on interest, which is generally, you know, I mean, it's a lot of money. They make tons of money, right? Banks make lots of money. But, you know, they're losing about, you know, whatever the interest rate is based on these things. So maybe like $100 a month or something in interest based on some kind of loan or credit card. Whereas the false negative means the person says, I'm not going to pay you back. You know, I owe you $10,000, but you're going to get zero of it, right? Or I'm going to declare bankruptcy and I can't pay anybody back. So, so the banks really do not like these false negatives, okay? And so a lot of times banks are very cautious. Now what happened in the 2008 housing crisis and financial crisis globally was that the banks got a little bit greedy, okay? And they said, you know, we don't have any false positives, right? I mean, we've got a lot of false positives and we don't have very many false negatives. Let's be a little bit more risky, okay? Excuse me. and let's start lending to people who are a little bit more riskier, okay? And so they increased this. And then what happened was that everything was built on this cascade, and then so as soon as one chunk fell out, like everything fell out, and the whole world suffered because of that, right? Corporate greed. So so yeah, it's a problem if you've got too many of these things where you didn't flag them as going to default. And so anyway, it's hard. Okay. So what you can do is you can change things, and when you call predict, you can look at the posterior, and you can look at did I do this right? Maybe I did this wrong. Okay. Oh, actually, I wanted the second column. So we want posterior, we want the column for yes, okay? So posterior, we want the column for yes, and maybe we're gonna turn them away if their probability of default is greater than 20%. So right now it was at 50%, and so we can say, so this will be flag a potential customer as going to default if as too high a risk if the probability of yes is greater than 0.2. Okay, so we'll go ahead and we'll do it this way. And so what happens here? Okay, so so this is the diagram we have now, and so if I let me copy this image again. Okay, so now we will say too risky for the bank if probability of default is greater than 0.2. Okay, and so what this leads is we got 9432 and 138. No, hang on. Okay, we predicted that they will default, and they did not. So this is 235, and we predicted that they will default, and they did. This is 195, and we predicted that they won't, and they did, and this was 138. Okay, and so now my sensitivity this is still 3333, and this is still 9667. Okay. So the sensitivity here is now 195 out of 333, which is better, 0.5885855. And then the specificity, this goes down. (9432) out of 9667. 0.9756. okay? So now, you know, we've changed the threshold, and so now we've increased our sensitivity, okay? So we're now flagging more people as going to default, okay? Which means our specificity, you know, more people are getting declined for applying for a new credit card or something like that, right? And you know, there's trade-offs here. Okay, you can't win them all, but this is what we have. And so this can be done by, you know, taking a look at which column is yes and no, and then drawing the threshold there. Okay, and so with the diagram, so here we used different thresholds of basically, you know, if we had a threshold of saying, you know, 0.5 versus 0.2 in terms of like when to flag someone as defaulting, and which one is our specificity and which one is our sensitivity, okay? And so here, let me, I'll copy this. Okay, so this line, whoops, okay, this line we saw the specificity go up, or I'm sorry, sensitivity, and then and over here the specificity is over here. I'm sorry, the red dot, this is specificity. And then the black line is overall error. Okay, so, you know, if we say we flag someone as going to default if they're over like 0.01, then now we're going to make huge errors, okay? We're not going to make very, our sensitivity, kind of our, this is, I guess this is, technically this is 1 minus the specificity. Oh, and this is 1 minus the sensitivity, technically. Okay. All right. So we have that. So you have those diagrams. And then lastly, we have this thing called the ROC curve. And I'll add this in. Okay? And so the ROC curve plots against the false positive rate versus the true positive rate. Okay? A worthless classifier will just be a diagonal line. Okay? And then the perfect classifier will go all the way to this corner, okay? The perfect classifier, a perfect classifier goes up to this corner and goes flat, okay? And then this is the worst, and this is a perfect one up here. It goes like this, okay? That's perfect. All right, and basically, the closer you get this part into the corner, the better the plot is, okay? Okay, so, you know, the different thresholds are not actually shown, but so the true positive rate, this is kind of the sensitivity, okay? And so what we want is that as we want the true positive, okay, to go higher and higher, but at the same time, we don't want we don't want to increase the false positive rate too much, okay? And so what we want is we want to be able to increase the true positive rate without really increasing the false positive rate, okay? And we actually get something pretty good, okay? Our false positive rate, okay, if we looked at just kind of the results that we had, you know, it went from like almost no false positives in our original setting, and then when we changed the threshold to 0.2, you know, our true positive rate went up significantly, okay? But and then the false positive rate did go down a little bit, okay? Or, I'm sorry, the specificity went down, so our false positive rate went up a little bit, but it was something like this, okay? And so we can keep changing the thresholds, and if we keep changing the thresholds, our true positive rate will still probably keep going up and up, but at some point, so this is like flagging everybody where the probability of default's over 0.2, flagging everybody where the probability of default's over 0.1, flagging everybody where the probability of default is over 0.05, okay? As we lower that thing for our tolerance of risk, you know, our true positive rate gets higher and higher, okay? But at the same time, the trade-off is that now we're starting to flag more and more people who would be good customers as people who are going to default, okay? And so at some point, it pushes, you know, the increase in true positive rate results in big increases in the false positive rate until we push it down to our threshold being 0, okay? And that's no good. Okay, and so this is the ROC curve. I'll add that to our notes and talk about that. Okay, so this is, we'll wrap up here today. I think there's just a tiny bit left. In the textbook, there's something, it talks about QDA. QDA, just rather than assuming all the sigmas are the same, quadratic discriminant analysis says the variances can differ from one class to another, okay? But again, we just let the computer do it, and you just type in QDA rather than LDA, and it works, okay? And then there's a few other things that, you know, be sure to read, and then and I'll create a homework there. Okay, but we'll wrap up here today. I guess you guys have a short break before the TA comes in, and we'll work through the lab with you guys. Okay, with that, we'll see you guys on Wednesday.